Welcome everyone back to the final talk for today's workshop. So we have Mark Zhandry telling us about revisiting post-quantum Fiat-Shamir.
Yeah, thanks for inviting me. And just a word of warning, I'm sharing a 900-foot home with a baby who might be making noise at some point. So yeah, bear with me. Okay, so I mean, we've been talking in the previous two talks about the random oracle model and the quantum setting. And just more generally, there's an issue that we have all these great lattice crypto papers, but lattice crypto isn't necessarily the same as post-quantum crypto. So even though we have that the underlying lattice problems are presumed hard, in most works in the lattice crypto literature, the security proof is a classical reduction which shows how to convert a classical attacker into an algorithm for those problems. And if you combine the two of these together, it does not yield the desired security goal in the post-quantum setting necessarily. What you need for this is actually a post-quantum crypto theorem, which says that you can convert any quantum attacker into a quantum algorithm for lattice problems. And then you combine this with the assumption that these lattice problems are quantum hard. And then indeed you would get the desired security goal. So in the sense of post-quantum crypto, most of the lattice crypto literature is on the left here in this rickety, leaky tower, giving just a classical reduction. And where we really want to be is on this nice grand castle on the right over here, where we actually have a quantum reduction. Now, it turns out that the good news is the vast majority of proofs, it's basically trivial to update the classical reduction to a quantum reduction. You can just go through and replace every instance of probabilistic polynomial time with quantum polynomial time, and everything will sort of magically work. But there are some key exceptions. One that we've already been seeing today is this quantum random oracle model. And another one that I will also be talking about is something called rewinding. Okay, so this talk is going to be, so this is the general picture of sort of where this paper lies. And for this talk in particular, I'm going to be talking about signatures. So how do we build signatures from lattices? Well, there's a couple main ways you might try to do this. So one is to build, lattices give you a one-way function, and we know that one-way functions actually imply signatures using some nice theoretical work from a few decades ago. And the good news is that this nice theoretical work is this sort of straight and easy path, and you can update, you can basically replace PPT with QPT, and you get a quantum proof. Another category of signatures is those based on the hash and sign paradigm. Here, it's a little more complicated. So there's some works that have shown how to instantiate this hash and sign paradigm in the standard model. And here again, it's relatively straightforward to just sort of update the proofs to work with quantum attackers. On the other hand, there are other signatures of the hash and sign variety that only have security proofs in the random oracle model. And so here we have this one barrier to proving security. It's certainly not trivial, but this particular case was sort of the first type of scheme that we ever knew how to prove in the quantum random oracle model. And we have a pretty good idea in general of how to handle this. So while there was this barrier, it's been pretty much solved. The last type of, question?
Yeah, Vinod. So when you say signatures with a quantum attacker, do you mean that, do you mean that the attacker can make quantum signature queries? So I can give you a superposition of messages, and is that what you mean?
For this talk, I'm only considering classical signing queries, which is that the attacker has a quantum computer. Handling quantum signature queries is actually, that one is non-trivial, that there is no sort of straight path. But for probably most real world applications, we don't care so much about attackers that can make quantum signature queries. For the most part, we're probably okay restricting the attacker to making classical queries, but we're concerned with an attacker who might possess a quantum computer to do computations on the side.
Right. So in the standard model, things should be okay. And in the random oracle model, you have to deal with the quantum random oracle, perhaps.
Right, right. And as we'll see, the random oracle model isn't the only barrier. There is also a barrier of rewinding, which we'll talk about in this talk. So well, that'll bring me to the last main category of lattice signatures, which is to build your signature scheme using the Fiat-Shamir transformation. And here we actually see both barriers. Both the Fiat-Shamir transformation is a random oracle model transformation. And then, as we'll see, proving the original security of the protocol, the interactive protocol you begin with before you even apply Fiat-Shamir, that protocol is going to involve a rewinding step in its security proof. And this is going to be a problem for quantum attackers, for quantum reduction. So there have been a number of works showing partial solutions to the Fiat-Shamir problem in the quantum setting, either showing how to get around rewinding or to get around this random oracle model business. But if our goal is to sort of work with the unmodified Fiat-Shamir applied to, say, Leibniz signature scheme, or many of the schemes based on it without modifying them, there are these barriers. And I should note that the modifications used to remove these barriers usually result in a reduction in efficiency. So there is a sort of a practical importance here. So in this work, we show how to get around both barriers. So first we show that Fiat-Shamir is post-quantum secure in the random oracle model. And then we also give new techniques for quantum rewinding. And by combining our theorem with these new techniques, we can show that, for example, Leibniz's signature scheme from lattices is actually post-quantum secure, assuming learning with errors, but making no modifications to the protocol. So this is the summary of this work. And I should mention that the left half of the work was actually, there's a concurrent work that appeared simultaneously with this paper that did the left half, and I'll actually compare our works a bit more later on. But the right half was sort of unique to our work.
Yeah. One more question. So you're saying are you saying there are really two things here? One is to prove that an interactive protocol is like, Lubashevsky, for example, is sound. That potentially uses rewinding, and then you need to deal with it. And two is actually assuming it is quantumly sound, compile it with the random oracle model. That's the second step. Okay.
Exactly. Okay, so with that, let me go into the quantum background. Now, you have seen two quantum random oracle model talks already, but I want to put a little investment in talking about quantum in a particular way, and it will pay off later because it'll make describing our results a lot less complicated. So to motivate the background, let's imagine a sort of simple model of a stochastic process, a classical stochastic process, where we have some system that starts out in a certain state, and I'm going to imagine the states being represented by these slots in the walls here. So I have a classical system that starts out in some state, and then I operate it on some way, potentially probabilistically. And I'll take another snapshot at a later point in time. And what I'll see is that there's some transition probabilities that say, what's the probability that the starting state goes to the first slots here at this later point in time, or the second, third, fourth, fifth. And then I can operate on it more with another probabilistic process, look at the state again, operate on more, look at the state again, and so forth. So in doing so, what happens is my state sort of goes through a path through all these, through this picture here. And these paths are, this notion of a path is going to keep coming out throughout the talk. So in the classical setting, we'll just think of you could imagine, for example, concretely, like I actually have a particle and it's traveling through the system and actually going through these plots, or you could think of it more abstractly as just a general process. But thinking about a particle is kind of nice because you actually then, what the particle does is exactly the path it's on. So I'm going to define this notion of a weight for a path, which is just the product of all these transition probabilities on the path from start to finish. And because this is actually just the probability that my system will follow this path. Now, let's suppose I decide to look at my system at some later point in time, and I want to know what the state of the system is at that time. And I'll see that it's in some state Y. What's the probability that I showed up in Y? Well, you can easily convince yourself that the probability that I land in Y is just the sum over all possible paths from S to Y of the weight of those paths. Okay, so I haven't done anything interesting yet. What gets interesting is how we interpret quantum in this view. So when I switch to quantum, a couple interesting things are going to happen. So first, my transition values are no longer going to be probabilities. They're going to be complex amplitudes. So they can be minus, there can be negatives, there can be things that aren't even real. So I'm going to replace my real valued probabilities with these complex amplitudes. But I'm still going to define the weight of a path the same way. It's just going to be the product of the amplitudes or weights over these paths. So this means, though, that the weight of a path isn't necessarily a non-negative number. It can, in general, be a complex number. So how do I go from these weights to actual probabilities? Well, if I'm going to view my system at a later point in time and actually learn what the state of the system is, what I will see is that the probability of landing in a particular state Y is no longer the sum of the weights of all paths from S to Y, but it's actually the sum, and then I take the absolute value and square it. So this is mathematically the change going from classical computing to quantum computing, is I replace non-negative real probabilities with complex amplitudes, and the way I go between those and probabilities is to do a square. Okay, so this view, I actually really like it because it makes a lot of the phenomena that you may have heard of in quantum computing, it actually makes it very easy to explain.
Mark, there's a
yes.
question. Why are you taking the square of the sum instead of the sum of the squares?
Good. So if I did the sum of the squares, I actually would just get back classical stochastic process. And the reason that we do it this other way, this is derived from physics, so I won't really go into that. But this is, once you derive from physics the mathematical abstraction of quantum computing, this is what you would get. Maybe one way to think about it is, if you're familiar with this, like the double slit experiment, which was one of the early experiments predating quantum mechanics. The point is that these paths were actually the paths that actual particles went on, and the observation of the value Y was really something like looking at the energy or the energy of a detector or something like that. And the way you go from something like an electric field to energy is you do involve a square. So there's sort of some physical intuition for why the square comes up, but for this talk, just think of it as sort of the mathematical model of what quantum computing is.
So Mark, so if you
yeah.
just like what was just, if you take the absolute value of the weight of a single path, then it's a product of absolute values of each of these like transition numbers, which is it then becomes probabilities, really, right? That's
right. So if I did it in the other way, there's really nothing different about quantum and classical, except that I, for some reason, represented my probabilities by complex numbers whose square is that probability. But by doing things in this way, where we take the square at the end, we actually get a number of interesting consequences.
I guess in particular, this captures some kind of interference that the other.
Right. So here's kind of the main intuitive difference between quantum and classical, is that because of this squaring, first, you can actually have these paths interfere constructively, and actually you sort of get more than the sum of either path, because you end up taking the square after you sum. And you can actually, because the weights on these paths can be negative, you can actually have destructive interference and have a bunch of different paths with high weights lead to a particular value, but then all the paths interfere destructively, and you actually never will see that value.
Mark, can I just
yes?
ask? Sorry, this is Rachel here. I just want to ask a quick question. Can I view these different layers as applying different sort of these quantum operations on these particles?
Yeah, so I'm thinking of it roughly as you sort of apply some operation. This could be an elementary gate, or it could be something more complex. You apply an operation, sort of talk about what the state of the system is, apply another operation, talk about what the state of the system is, and so forth.
Okay.
Okay, so what are some consequences? So here's one consequence. Let's go back to the stochastic setting. And let's suppose I don't just observe the value y at the very end, but also at some intermediate point I observe the value x. What's the probability of observing both x and y? Well, it's relatively easy to see that what you do now is you just sum the paths from S to Y that also go through X. And now let's suppose I observe X and I observe Y, but now I forget X. So what I do is I marginalize out the variable X by summing over the probabilities, by summing over all X of the probability of X and Y. And routine calculation shows that you indeed get the probability of Y back that you started from. Okay, this is totally unsurprising. But what happens when you move to quantum is something actually very interesting happens. If I observe X and I observe Y, the probability of X and Y is what you would expect. It's the probability, it's the sum of the weights of all paths from S to X to Y, that's sum squared. But here, if I observe X, I observe Y, and then I forget what X was. So if I try to marginalize out X, I take the sum over X of the probabilities of X and Y. If I write out the expression, I will see that it certainly does not match the probability of observing Y. So what on earth happened? Did I just disprove quantum mechanics? No. What happened is that observing X meant that so I have all these paths potentially going to Y, and these paths going to Y travel through different X. But when I observe X, now I've forced those paths to no longer interfere, because I've sort of resolved which X the path is actually going through. So the paths for different X can no longer interfere. And what this leads to is the observer effect, or it goes by many names. I'll call it the observer effect, which is that if I learn anything about a quantum system, I actually am necessarily disturbing it. So by learning what X was, even if I later completely forgot what X was, I'm actually changing the probability distribution over my later observation Y. So here's another potentially interesting consequence. So you may have heard that quantum mechanics is reversible. Why is it often said that quantum mechanics is reversible? Well, in order to make the math work out that that the square of these probabilities, the square of the sum of the path weights actually gives us a probability distribution, it turns out that the transition matrices, so the matrices that I get by taking all of the transition weights and assembling them into a matrix, turns out that these transition matrices have to preserve two norms. which implies that they're unitary, and unitary matrices are invertible. So this means that the sort of basic operations of quantum mechanics going between these layers are invertible operations. But we also have this extra thing called a measurement or an observation. And when I actually observe the state and learn which state the paths are going through, as we just saw in the previous slide, I'm actually irreversibly altering the state. So in some sense, quantum mechanics is actually inherently irreversible once I throw in measurements. And this will be very important later. On the other hand, you could ask the same thing about classical mechanics. So in the classical stochastic view, we also get a condition on what these transition matrices look like, and it turns out that they have to preserve one norm. And these types of matrices are called stochastic matrices, but stochastic matrices in general could be singular. There's no guarantee that they're invertible. So this might suggest that classical mechanics is irreversible, whereas quantum mechanics is reversible. But remember that with classical mechanics, we can always observe the current state at any point in time, and this does not affect the trajectory of the system. And what this means is, in some sense, we can always turn a classical process that might have been irreversible into one that is reversible by recording our state at any given point in time, and then if we ever want to return to it, we can just go back to it. So in some sense, the classical stochastic process is reversible as well, and so we will touch on this difference later. So I actually like to think of quantum mechanics as being irreversible and classical as being reversible, which is the opposite of what you may normally hear. Okay, so that's the background on quantum that I wanted to talk about. So now I want to get into the first part of the talk, which is Fiat-Shamir in the quantum random oracle model. Okay, so here's the Fiat-Shamir transformation. We'll think of it as a transformation from 3-round public coin honest verifier proofs of knowledge into non-interactive proofs of knowledge. And how do you do this? You do this by simply setting the verifier's message. Because it's public coin, you'll set the verifier's message to just be the hash of the first prover's message. So I'll call the first prover's message the commitment, the first message from the verifier the challenge, and then the last message the response. So I set the challenge to be hash of the response using some hash function. And so this we'll think of it as being a way to compress the rounds of proofs of knowledge. It's also a way to turn identification protocols or proofs of knowledge into signatures. So the problem with Fiat-Shamir is we don't know how to, in general, base the security on collision resistance or any simple property of a hash function. So we have to treat the hash function as a random oracle. And how does Fiat-Shamir work in the random oracle model? So let's suppose we have an adversary that can, so how do we prove soundness? We assume we have an adversary that generates a valid proof after making some queries to the random oracle. What we're going to do is we're going to turn this adversary into one that actually breaks the interactive protocol. So classically, how does this work? What we're going to do is we're going to select a random query, a random one of the random oracle queries that the adversary makes. Let's call it I star. So when the adversary makes his queries to the random oracle, on all queries but the I star query, we're just going to simulate the random oracle by choosing a random value and replying with that. The interesting thing happens on the specially chosen query I star. Here we will take the adversary's input that they submitted to the random oracle query, and we will interpret that as the first message in the proof, and we will send this to the verifier. So we'll send the I star query to the verifier. The verifier will respond with a challenge, and we'll just program the output of the random oracle on the I start query to the whatever this challenge was. And then we keep going. Eventually, the adversary outputs their Fiat-Shamir proof. We just check that we basically guessed the right I star. We check that their commitment was the one that we got from their I star query, and we check that they used the same challenge. And you can analyze this and show that you succeed. That if the adversary succeeds, then the response must actually be a valid response to your interaction with the verifier, and that this doesn't happen with too small a probability. So this is the classical reduction idea. But of course, now we're talking about quantum attackers, and in the real world, this random oracle is a hash function that the quantum attacker can interact with using quantum interactions. And so the only thing that makes sense to do is to allow our random oracle model attacker to also query the random oracle using quantum interactions. So we need to come up with a proof that works in this quantum random oracle model. But there are a number of problems with doing so. And to illustrate those problems, I want to sort of describe what a query algorithm looks like in this path view of quantum computing. So in this path view, what I will imagine these various snapshots in time are the various queries the attacker is making to the random oracle. And then the final snapshot of the algorithm is just going to be whatever he outputs. So the way, remember I said that quantum operations have to be unitary. So the way that, so I need to actually model a query as a unitary operation. And the way this is generally modeled is that the query input is actually a domain element of the hash function and some value y in the range of the hash function. And the query operation XORs h of the domain element into the y value. All right. So what's the problem with Fiat-Shamir in the quantum random oracle model? So the first problem is that if you think about the classical proof, at some point I actually had to observe the attacker's query in order to get the commitment that the reduction sent to the verifier. But remember that we have this observation effect, which says that observing this commitment actually is going to disturb the attacker's state. And maybe at this point, the attacker just decides to stop working. Maybe we disturbed him in a way that he will no longer operate. Then we will not actually be able to complete the protocol because we'll never get a good response out of him. Another issue is the usual on-the-fly simulation of the random oracle. And the reason is that the attacker can basically send paths through all possible inputs to the hash function, and then later on try to manipulate them and get them to interfere with each other in some way. So in some sense, the entire trajectory of the attacker is affected by all domain points of the random oracle, even if he only makes one query. The way this is usually fixed in the QROM literature is to commit to the entire hash function at the very beginning of the reduction and never change it, or maybe only change it very selectively. But this is going to open up yet another problem, which is not only do we need to extract this COM value from the attacker, but then we need to program the random oracle with whatever response we got. But the problem is we don't know what COM is until we're midway through the reduction, at which point, if we use the typical solution, we've already committed to the entire description of the oracle and we can't change it. So somehow we have to figure out how to adaptively program h of COM I star to be whatever challenge we got from the verifier mid-execution. the bulk of the QROM techniques do not let you do this. So our main theorem says, actually, you can get around this. So Fiat-Shamir preserves knowledge soundness in the quantum random oracle, and it also allows you to construct signatures from identification protocols. I'm just going to jump right into the proof idea. So our proof is going to build on some work of mine, also from last year. So the first step, this part's not really the interesting part, but the first step is that we're going to replace our random oracle model. So our random oracle, which just assign an equal probability to all possible functions. We're going to replace this oracle with a quantumized version that puts equal weight on all possible oracles, but now this oracle is itself actually a quantum state. And this doesn't cause any effect on the adversary's output, because basically this oracle is outside the adversary's view for the entirety of the experiment, except via the queries. And what this means is that the paths for different oracles can't interfere, because the oracle state is sort of outside of the adversary state. So doing this transformation has no effect on the output distribution of the adversary. But what it does is it allows us to actually extract some useful information. So in this prior work, I don't describe the result using this path terminology, but the path terminology is actually makes the statements of the sort of main idea very concise. So what I'm going to do is, remember, I'm thinking of a path of the attacker as their path through all these snapshots in time, which are their queries. So if I were to take the this quantumized random oracle and look at it in what's called the primal domain, so if I were just to observe it, what I would just see is the hash function h, and that's not that interesting. But what I can do is something called the quantum Fourier transform, and I can actually observe the oracle in a different domain called the Fourier domain. And if I were to do this, what I would see is actually some partial information about the current path that the adversary is on. In particular, what I would see is this function that I'll call the parity of a path. So the parity of a path at a particular point x is going to be, what I'm going to do is I'm going to look at all x-y pairs along the path, and I'm going to XOR the y values together. So all x-y's where the x is whatever point I'm looking at. So for all x-y pairs where the x is the particular input that I care about, I'm going to XOR those y's together, and I'm going to call this the parity of that given path at the point x. So if I were to look, yes, question?
I understand this definition. So x is a point in the path, and I'm
x
looking
is a point in the domain of the random oracle, and I'm imagining the points in the path are pairs of input-output pairs of the random oracle, and the way I process the random oracles, I XOR the output into the output.
Okay, all right, sounds good. Yeah, that's good.
Good. So what sort of, it's basically just a simple consequence of what it's one of these Fourier transform input-output rules. But basically, what ends up happening, if you look at this quantumized random oracle in the Fourier domain, you actually magically see this partial path information for every domain element of the random oracle. You see the XOR of the corresponding y values from all XY pairs on the path. Okay, so this is going to be our starting point. And what we've proved is here's this informal lemma, which roughly says that if the parity of a path at a particular point is identically 0, then the path actually has no knowledge of the oracle at that point. This is informally stated, you know, with a more precise meaning. But it roughly says that if my path has, so certainly this is true at the very beginning. At the very beginning, the parity of a path is all zeros. And if at any point the parity of my path is zeros at a particular point, then that path has no knowledge of the oracle value h of x. So a couple corollaries. One is that if I have a successful path for the adversary that actually generates a proof, a valid proof, the valid proof includes the oracle value of h of the commitment. And so that means that parity path, the parity of the path evaluated at the commitment that they ultimately output actually had to be non-zero by the time they reached the end of the interaction. So how are we going to use this?
Mark, a question.
Yeah.
So this could either happen for the trivial reason that X does not occur in any of the states that that you query, or there are sort of 2 points where X occurred, but they sort of interfered with each other. Does that?
I mean, it's not so much that it's not even interference. It just might be I query on a particular XY, and then I query on the same XY again.
Right. That's right.
Yeah. So so what this shows is that I could have at some point in time known what h of x was, but if at a later point in time I make the parity of my path at x0, it actually means I don't know what h of x is anymore.
Yeah.
So another tool we're going to need is something I'll call the observation lemma. This is something we proved back in 2013. I expect some versions of it were widely known in the quantum crowd. But it basically says that while observing X can have an effect on the output distribution of a later observation Y, it says that it can't mess it up too much. In particular, if I knew that X gave one of T possible outcomes, then observing X can only reduce the probability of any particular output Y by a factor of T. So this is actually just a really simple consequence of, call it what you want, Cauchy-Schwarz, Jensen inequality, or just norm, the relationship between one norm and two norm. It's basically, in one case you have the sum of squares, in the other case you have a square of a sum, and the relation between those, the ratio between those can't be more than the number of elements in the sum. So if I observe X, and then later observe Y, the probability of observing Y couldn't have gone down except by a factor of T.
So the left probability is average, right? So it's like on average over X.
Yeah, so I observe X and then I forget what X was.
Okay.
Yeah. Now note that this doesn't work in the other direction. If I were to observe X and ask what the probability of Y is, and then I don't observe, then say, okay, well, let's say I actually didn't observe X, I can actually get an infinite increase in particular Y values. So this is only it's only a one-way thing, showing that going from not observing to observing can only reduce by a factor of T. So what we do roughly is we generalize this to talk about general paths. So if it were possible, so imagine we have a partition of possible paths. Maybe the partition is based on which state the path goes through at a particular snapshot in time, or maybe it's a more general partition. If I partition all possible paths, and imagine that I can observe which element of the partition I am in. If I do this observation, again, it can only decrease the probability of any ultimate outcome by a factor of T, where T is the number of sets in my partition. So this is just a sort of a straightforward generalization of this observation lemma. So what we do is we describe a collection of partitions, or we describe a partition, so a collection of sets of paths that will allow us to do query extraction. So we'll just focus on successful paths, so paths where the adversary actually succeeds. We would also have the non-successful kind, but we don't have to worry about them. So amongst the successful paths, how are we going to partition? Well, we know that a successful path has to start out at having the parity being 0, because the parity is just 0 everywhere before you make a query. And at the end, the parity of that path has to be non-zero, because you have to actually know the hash value in order to output it. So what the partition will do is we'll partition the paths by the last time the parity of the path at the COM value transitioned from 0 to non-zero. So PI is a set of all paths whose final time transitioning from 0 to non-zero is at query I. And we can actually sample from these PIs. There's a little caveat that we actually have to, we can sample, we can do the measurement of the PIs, but only assuming we know what the output of the measurement is going to be. And so in order to actually make this work, we have to guess which I we're going to get. And then if we guess wrong, we just abort and we lose. And this having to guess what I we're actually going to get causes us to lose an extra factor of Q, the number of queries in the reduction. But assuming we knew which I we were going to get, here's how we measure I. When making the ith query, we observe COM. We observe if the parity of the path at COM was 0 just prior to evaluating the query. If it's not 0, we know the path actually isn't in PI and we just abort. And otherwise we continue. And for every later query, we check that the parity of the path remained non-zero, and if it ever goes back to 0, we abort. So this has the effect of at the end of the whole experiment, we've selected, if we don't abort, we're actually exactly where we want. We have exactly just the path in the set PI.
Mark, just observing is still conceptual like in the classical setting, or is there actually a measurement involved?
So there actually is going to be a measurement here. Right, but the point is that if we're on this set of paths, then COM actually is effectively measured at query I already. And so the fact that we're observing it, right, our observation of this COM just means we sort of write it in some other space. And yeah, if I wanted to be complete, I would need to do a couple more slides to make sure that this works. But you can nonetheless show that you get exactly what you would hope for if you were actually measuring the I value from the path partition. But yeah, it's actually, but the whole reason we did all this is exactly so we can observe the COM value without hurting our probability of success by too much. Right. So now we have the COM value, but we still have the second problem about how do we embed the challenge into the random oracle. So here we're going to have a new idea, which is, well, we said that just before query I, the parity of the path at COM is 0. And by our lemma, this means the adversary knows nothing about h of COM. So what we should be able to do is just replace h of COM with whatever we want and be happy. In particular, we can replace it with the verifier's challenge. The problem, though, is that now we've reclassicalized the value of the oracle at the point COM. And so we have no more access to the Fourier domain with which we were evaluating the parity of the current path. And remember, we actually need to know what the parity of the path is at the point COM in order to do our partitioning correctly, because we're saying that our paths are all those whose parity path at COM is non-zero after the ith query. So we need something better. And what we're going to do is we're going to do an alternate set of paths where, well, okay, so here is just, we could have imagined partitioning by saying we have success by saying it's not, by looking at the I where it's the first time we made the transition from 0 to non-zero rather than the last time. So this is another partition of the paths. But this partition doesn't work. We can't actually efficiently sample from it. because in order to carry out this partition, we actually need to know what COM is at the beginning in order for us to evaluate parity path of COM at all queries before the ith query. But the problem is that we haven't actually observed what COM is until the ith query. So this partition doesn't really work. So the takeaway is we need a partition that doesn't check parity, the parity at COM once programmed, because once programmed, we lose access to this Fourier domain. At the same time, we need a partition that doesn't check the parity before the ith query, before COM was observed. So what this leads to is a different set of paths, which I'll call QI, which are the successful paths that were 0, where the parity was 0 just before the ith query and became non-zero just after the ith query. So this satisfies both things that we want. So by being 0 before the just before query I, but we don't care what it was and on all the queries preceding I, we don't need to know what COM is until query I. And we also don't care about the parity anymore after I, because all we care about is that it transitioned from 0 to non-zero at I. We don't know what happens at all the other points of I. So it's fine that we lose access to the parity. The problem is that these QIs are not actually a partition, and they overcount paths that go back and forth many times. So if you go 0, non-zero, 0, non-zero, you'll actually be counted twice in 2 different QIs. So we don't get a partition, and therefore there's no way to apply this observation lemma or this generalization of it. So what we do is we actually come up with yet another set of paths that turns out to exactly correspond to the overcounts of the QIs. And this other set of paths are those where on query I, we go from non-zero to 0. And remember that we're talking about successful paths here. So the overall path still has to, in net, go from 0 to non-zero, but these RIs will be triggered when you go from non-zero back to 0, somewhere in between. And you can sort of test for yourself that any occurrence in RI corresponds exactly to its overcount in the QIs. And we in fact give another generalization of this observation lemma that I won't go into the details here, but it basically says that this works. That by looking at, by having something that overcounts, but then something that exactly corresponds to the overcount, we get exactly what we want. And that's basically the gist of our result. I do want to briefly mention how we relate to this concurrent work by Dawn, Fair, Magins, and Schaffner. So in our work, we actually, I lied a little bit. Our set of RIs, these compensating sets that I added after the fact, is actually much larger. It's cubic in the number of queries instead of linear. And therefore, we actually get a terrible reduction. The concurrent work didn't go through anything with paths or anything like that. They actually gave a very direct algorithm and analysis that just sort of magically worked. But it turns out that their algorithm is essentially the same as ours. We only realized this after the fact. Their algorithm is essentially the same as ours, but with the RI I just presented on the last slide. And because this set of RI only has Q elements, basically we only lose Q squared 1 because we have to guess the measurement outcome at the beginning, and then another one because of the hit from the observation lemma. Okay, so that's it for our QROM. And I just wanted to, briefly say that with some of the recent advances in the QROM literature from the last couple of years, most major random oracle techniques have now been ported to the quantum random oracle in some way. And so there's actually seems to be good reason for optimism that the quantum random oracle model is very close to the classical random oracle. It's just a lot harder to actually prove anything. And the fact that we have all these new techniques now perhaps explains why the known counterexamples are so contrived. We actually only know 2 counterexamples. One from our original work in 2011 relies on a certain weird timing model that's artificial. And then another more recently gives a counterexample of a scheme secure in the ROM but not the QROM, but it doesn't correspond to any natural crypto task. And so it's a sort of an interesting question whether there actually is any separation here.
Oh, Mark, what do you mean
yes.
by time?
What do I mean by what?
Timing. What is timing?
I mean that what we give is an identification protocol where the verifier actually counts how long it took the prover to respond.
Oh.
Which is not the normal model for an identification protocol where we imagine everything is sort of asynchronous.
Mm-hmm. 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 I see. So you're
okay.
saying sort of a side channel thing? You're saying if the verifier knows how long it takes for the prover to return an answer, then he can break it in the QROM model. I'm not sure I completely understood.
I mean, the gist is just that in the quantum random oracle model, you can use something like reverse search to get a polynomial speed up. Right. And so what this allows you to do is to solve certain tasks a bit faster than what could be done classically. And then you use the timing. The verifier will check that you solved the problem faster than any classical algorithm could do, but a quantum algorithm can do it and cheat.
I see. Okay. Okay. Mm-hmm. All right.
All right. Okay. So in the last several minutes, I will go to the second part of the talk, which is our new techniques for quantum rewinding. And here's the problem. How do we prove knowledge soundness of an interactive protocol? Well, usually what we do is we start from something that's easy to prove called special soundness, which says that given any two transcripts, such that the transcripts are different, but the first message is the same, that you can actually extract a witness. So this is special soundness. And in the classical setting, special soundness implies knowledge soundness. What's the classical reduction? Well, let's assume we have an attacker that convinced the verifier. What we're going to do is we're going to run the attacker once, and then we're going to rewind them using the fact that classically we can basically always save state and return to it at a later point. We're going to rewind the attacker to just after they made their commitment and then run them again just on a fresh challenge. And the result is that we'll get two transcripts that both verify and have the same first message. And therefore, from these two transcripts using special soundness, we can extract a witness. So any prover that convinces the verifier, you can then extract a witness from, just based on the special soundness, which again is typically very easy to prove. When we move to quantum, though, extracting the first response, right? So if I go back to here, extracting this first response in the quantum setting is going to irreversibly alter the adversary state. So we actually can't return to their immediate post-commitment state. And what this means is that we don't get a guarantee that the adversary works when we submit a new challenge. This problem was first observed by Van de Graaff a couple decades ago, and was formalized more recently with an actual counterexample. And we have a couple counterexamples. One is relative to a quantum oracle, one is relative to a classical oracle. These are, we actually, interestingly, don't have any standard model counterexamples, but nonetheless, it represents a proof technique barrier. So the good news is, again, that we don't have any standard model separations, no known ones. But the bad news is that we don't know how to prove anything just from special soundness, and it's actually not enough to prove anything. We have these contrived oracle-based counterexamples. So in order to prove soundness, we're going to need to add some additional properties to our proof. And there have been a number of works doing this in the past, but they all basically involve, they all require modifying the existing constructions in some way. And these modifications will generally result in reduced efficiency. Right, and in particular, right, none of the examples apply to, say, like Lubashevsky's scheme or any of the efficient schemes based on it. So I'm going to go, I guess, rather quickly through the remainder of my slides, but so the basic idea is that we're going to use a prior work of Unruh that more or less reduced the problem of constructing a proof of knowledge to something much weaker. So what does Unruh say? He says that if we only observe whether the adversary succeeded in the first round, but don't actually observe res, the response from the first round, he actually shows that rewinding works. And if you combine this with something that he calls strict soundness, which says that once you have the commitment and challenge fixed, that there's only a unique valid response, then you actually get security. Why? Because remember, I have this observation lemma, measurement lemma, that says that if I observe something and it only produces k possible outputs, then the probability can only be reduced by a factor of k. Well, in this case, k is going to just be 1 because there's only a unique response. And so once I already guaranteed to have a valid, quantumized transcript, I can actually observe the response, and I won't affect the success probability. And so you actually get knowledge soundness. And the problem is, how do you guarantee this strict soundness requirement?
Mark, it's Hotek.
Yeah.
Since the last talk, I think it's fine if you go over time, so it's okay.
Okay.
To go slower.
Okay. I mean, I also have my own time constraints, but
I see.
Right. So if we assume that rewinding works if you don't observe the response, and you have this strict soundness guarantee, then you actually get knowledge soundness by applying this observation lemma. So what Unruh shows is actually this weaker guarantee holds. If you don't observe, this weaker guarantee holds in general. So if you don't observe the response, but you just observe whether the first run succeeds, you actually get the weaker guarantee. I won't prove it. My intuition, my own personal intuition, is that it's another variant of this observation lemma. It's certainly very different. I mean, it predated our lemma, but that's sort of my intuition that measuring a binary outcome does not change things too much. So to motivate our solution, what we're going to do is a brief segue into something called a collapsing hash function. So a collapsing hash function was introduced by Unruh a few years ago as a generalization of collision resistance. And what a collapsing hash function says is that if you take a superposition of inputs and you measure the output, so you apply the hash function to the quantum state that's your input, and you observe what h of x is, or you observe what x is. These will result in two different quantum states. But what a collapsing hash function actually guarantees is that they're indistinguishable. So what we do is we basically take this notion and sort of port it to the Sigma protocol setting. We define a notion of collapsing for Sigma protocols, which says that if I observe the output of verification, and additionally conditioned on if the output of verification is 1, I either observe the response or I don't, that the two cases are computationally indistinguishable. I give you the superposition of responses, and I either measured the response or I did not, but in either case, I measured whether the whole transcript verified. So this is a collapsing protocol. It says that these two are indistinguishable. And we prove it's essentially the same as Unruh. We show that this is enough to get knowledge soundness. So now we've reduced the problem to trying to find a collapsing Sigma protocol. And for this talk, I'm actually going to focus on a simpler problem, the simpler problem of finding collapsing hash functions. And it turns out that for, say, proving Lyabushevsky, this is enough. So what our goal is going to be is to prove that the cis hash function is collapsing. So this will be the last couple minutes is where I will actually finally talk about lattices. So what is the cis hash function? It's roughly you fix a large matrix A, and your domain element are vectors whose entries are short, and you just compute the inner product mod Q. So this is a hash function. It's collision resistant under the short inverse solution problem, which can be reduced to hard lattice problem. So we want to prove that this is collapsing. And now what are the existing collapsing hash functions? So a few works have shown that random oracles or various things derived from random oracles are collapsing. And then there's also a work of Unruh that shows how to build collapsing hash functions from lossy functions. Unfortunately, cis contains neither a random oracle nor a lossy function, so we're going to have to do something different. And our solution is related to the lossy function approach, but it's something called associated lossy functions. So if I have a hash function H, an associated lossy function is just it's some function f that can be generated in one of two ways. So what I'll do is I'll take an image point for the hash function, and I can either generate f in a lossy mode based on that image point, or in an injective mode based on that image point. And the guarantee is that in the lossy mode, this function actually maps all preimages of y to the same point. Whereas in the injective mode, the function has to be injective on the set of preimages. All right, so I can generate my function. So you give me any image point, I'll generate a description of a function f in one of these two modes that either maps all preimages to one point or maps all preimages to distinct points. And the guarantee is that when I hand you the description of the function, you can't tell what mode it was used to generate it, even if you know why. So what we show is that associated lossy functions are enough to imply collapsing. And the theorem proof is pretty straightforward. So on the left here, I have the case where you observe the output of the hash function, and on the right, I have the case where you observe the input. So I'm going to make some hybrids. So the first hybrid is I will observe the output of the hash function. I'll then generate a lossy mode function f and observe the output of f applied to my input. Because I generated f lossily, I actually know that the entire state of inputs actually all has to map to the same z value when I apply f. And so observing the output of f actually didn't change anything. This is just the measurement lemma again. And then I use the lossiness, the security of the associated lossy function to switch to injective mode. And then, but when I'm in injective mode, observing the output of f is actually the same as observing information theoretically is the same as observing x because of the injectivity of f. Because information theoretically, once I've observed the output of f, I actually must know what x is. So it is actually enough to give an associated lossy function for a hash function, and that will prove collapsing. So our theorem is that actually cis has associated lossy functions, assuming LWE. And the construction is exactly what you would expect. So remember, A is this matrix defining the hash function. To generate the lossy mode, I actually ignore the y value altogether, and I just generate a bunch of LWE, a matrix of LWE samples relative to A. And what is my lossy function? It takes this matrix, inner products it with the input, and does some sufficiently coarse rounding. And the point is that because the input to cis is short, and the LWE sample has a short error, that the sort of error part goes away, and I'm left with a value that depends solely on the output of sys. Meanwhile, to generate the injective mode, I just generate uniformly random samples. This is indistinguishable. So security is immediate by the security of LWE. And as long as I set my matrix to be tall enough, if I choose a uniformly random matrix, this function that maps x to b times x and in rounds will be injective. This shows that sys has associated lossy functions, and with our theorem, we now get that sys is collapsing, and with slightly more work, you can get that Lyubashevsky's protocol is collapsing and therefore complete everything. There's one caveat that the correctness of the lossy mode actually needs a super polynomial Q, which we don't want to rely on, especially because the most efficient protocols have only a polynomial Q. And so we show how to fix this. Basically, we need to relax the notion of lossy functions and show that that's good enough. Yeah.
So sys probably gives you pretty easily somewhere statistically binding hash function, right? And is that enough to? Is that an alternate path to get to collapsing?
Yeah, I mean, so constructing lossy functions is not hard, but we want to show that a particular hash function is collapsing.
Namely,
right? So you would need to show, right? So no, I mean, I'm sure there's many ways to show that sys has associated lossy functions, but just because you can use sys to build some collapsing hash function isn't necessarily enough.
So you want to show that the sys hash function, the a times x, is collapsing. Is that right?
Right, and with a similar idea, we can show that Lyubashevsky's underlying identification protocol is also collapsing.
I see.
But right, the reason we want to do this is we don't want to modify the existing protocol.
Right. In the proof, you want to sort of maybe make some mental experiment, change the distribution of A and so forth. But that's that you permit, yes? I mean,
yeah.
Okay, so here's I guess the other question is, so now the security of the whole thing is proved based on LWE, as opposed to I guess Vadim, which only required sys, right? I guess you could claim that if you break LWE, you break sys in the quantum world, right? But is that very? At the end of the day, you can base everything on sys quantumly. Is that right?
Correct.
Okay.
Yeah, but again, with whatever loss is needed to go between LWE and sys.
Sure.
So we potentially lose something in the reduction.
Sure.
Yeah, so the main takeaway is that actually, whereas before we only had basically two families of collapsing hash functions, my own personal takeaway is that collapsing hash functions and also probably collapsing Sigma protocols are actually probably much more common than previously thought, because you could imagine using totally crazy tools to try to build the associated lossy function to your favorite hash function. Use indistinguishability obfuscation or whatever you want. And actually, maybe this shows why finding a counterexample to collapsing is actually pretty hard. It's actually been, we don't have any standard model examples of a collision-resistant hash function that is not collapsing. And maybe this is why that it's actually very hard to try to show that no possible associated lossy function exists, even if you use crazy tools like I/O. And the reason I'm interested in this last question is that these counterexamples can actually be used constructively to build interesting quantum protocols like quantum money. So with that, I'll conclude. Thank you for listening, and I'll take any questions.
All right, let's quickly thank the speaker. And do we have questions? seems that we don't have questions. Maybe we can take questions offline. Maybe Mark, you can stay around for 1 or 2 minutes in case there are questions. And then I guess let's just thank everyone again.
Let's thank all this.